Alright, 2.6, day number 1 on continuity. I want to start off by talking about the checklist of items in order to have continuity on a function f of x at a point x equals a. So 3 items necessary are that the left hand limit as x approaches a of f of x equals the right hand limit as x approaches a of f of x. Which just implies that the limit as x approaches a of f of x exists. So on this diagram here of f of x as x approaches a from the right and left, that limit exists. Second requirement is that f of a must exist, as well as the third requirement, which is the limit as x approaches a of f of x equals f of a. So for that to be true, the limit has to exist, value has to exist, and the limit has to equal the value. Those are the 3 requirements for continuity on a function f of x at a point x equals a. Alright, so here's a graph. May not be real easy to see, but I do actually want this point right here at what looks to be 4, 2 to be open. There's a removable discontinuity here at x equals, I believe that's 2. We'll verify that in a minute. So let's look at a few values using both the graph and a few limits that we're going to look at here. So let's take a look. So f of negative 5 f of negative 5 equals 6. F of 2 equals, it looks like 1. Don't be fooled into thinking it's 3. It's actually 1. F of 4 equals, looks like 2. Let's go through a few limits here now. X approaches negative 7 of f of x. Negative 7. As we approach from the left and right, that looks like it equals 2. As x approaches 4, this limit for f of x does not exist. You can see that as we approach from the left and the right, those two don't agree. That limit would not exist. As x approaches 0 from the right, as I approach x equals 0 from the right, our graph is increasing without bound in the positive direction. Here, what we've talked about in the previous lesson, 2.5, this is a horizontal asymptote. If I'm looking at a limit at negative infinity of f of x, that's approaching 0, at least from what it looks like on my graph. Limit as x approaches negative 5 of f of x, that limit exists. That would equal 6. Limit as x approaches 0 of f of x is taking into account the 2 limits from the left and the right. That does not exist. As x approaches 4 from the right, that looks like, I can't tell from my graph, but I would say negative 2. Might look more clean on your notes, but that's what it looks like for me. As x approaches infinity from the right, horizontal asymptote at 0. As x approaches 2, that value may not exist at 2, but the limit does exist, which would be 3. As we approach 0 from the left, that's negative infinity. And as we approach 4 from the left, that would be 2. Now let's look at continuity in each of these cases at x equals negative 7, at x equals 2, and at x equals 4. In each of these cases, f is not continuous at those values, but for different reasons. So at negative 7, the limit, the requirement number 1 where the limit exists is in fact true. However, f of a, or in this case f of 7, negative 7, excuse me, does not exist. Right? It doesn't exist. Therefore, that's an infraction on that second checklist item for continuity. At x equals 2, the first and second items are true. The limit exists. It's 3. The value exists. It's 1. However, the limit does not equal the value. Therefore, the limit as x approaches 2 of f of x does not equal f of 2. Okay, and then at x equals 4, it looks like we have an infraction on the first rule because the limit doesn't exist at x equals 4. Limit as x approaches 4 of f of x does not exist. Okay, so that's just a general overview of continuity. Let's jump into a second example. Specifically here, where are the following functions discontinuous and why? Let's use the definition. So let's look at the limit first. Let's see if the limit from the left and the limit from the right are equal. Basically saying, does this limit exist as x approaches 2? So if I were just to kind of by inspection look at this, and I plug in a 2, that's 4 minus 2 minus 2, which is 0, and 2 minus 2, which is 0 as well. So I'm going to want to consider using one of my methods, and in this case I'm going to use a factor and reduce method. So I'm going to factor the numerator. It looks like I would get x minus 2 and x plus 1. That would allow me to reduce, okay, which would reduce this limit as x approaches 2 to x plus 1. Okay, and this limit itself, I'm not going to string equal signs along, would end up giving me a value, limit as x approaches 2 of x plus 1 would equal 3. Second item would be, well, what is f of 2? And in this case, f of 2 doesn't exist, right? If I plug in a 2 for this, I get 0 over 0. It doesn't exist. Therefore, the following function is discontinuous here because f of 2 doesn't exist. Infraction of the second part. Okay. All right, so moving on to the second example. If we look at the piecewise function 1 over x squared when x isn't equal to 0, and 1 when x is equal to 0, I'm going to actually just do this one graphically. I'm going to take a look at 1 over x squared, which looks like this. Right, horizontal asymptote at 0, vertical asymptote at, horizontal asymptote at y equals 0, vertical asymptote at x equals 0, but then an output of 1 when x equals 0. So the limits, first of all, in fraction right away, the limit from the left and the limit from the right tell us that we get positive infinity from the right and positive infinity from the left, which tells us that the limit as x approaches 0 of this function f of x does not exist, and therefore right away I know that it's discontinuous here because the first part of the checklist doesn't work. Okay, all right, let's look at the next one. Again, I can look back to part A, and I said in part A that the limit of this function as x approaches 2 is 3. Right, so I can say the limit as x approaches 2 of this thing, right, f of x, is equal to 3. I know that from the work I did earlier. Now, how do I know that I want to go as that to 2 with this function? Is because this is where a possible discontinuity might be. All right, how about the second part? Well, the second part is f of 2 equals 1. Okay, so at 2, the function output is 1. So the value exists and output exists. However, the limit as x approaches 2 of f of x does not equal the output at 2. Therefore, it's discontinuous there. So it's really a graph that kind of looks like, it looks somewhat like this. And this won't be entirely to scale, but there's a discontinuity here. The limit exists, the value exists, but the limit doesn't equal the value. Okay, and then if I look at the step function here, right, this greatest integer function, that should be open. Okay, this is closed, this is open, this is closed, this is open at values 1, 2, and 3. Okay, this would be 1 and 2. We're going to notice that there's a discontinuity at every integer. All right, in between integer values, continuous, but at every integer value, right, the one-sided limits exist, but the limit at the value doesn't exist. Therefore, direct infraction immediately. All right, let's keep moving on. Example 3. I want to talk real quick about right and left continuous, which is a thing. All right, so if I graph this piecewise function where function equals x minus 1 and x is less than negative 1. Okay, so here's the graph of that piece. And then x plus 1 when x is greater than or equal to negative 1. What you'll notice is that this part of the graph right here is right continuous, because as I approach this value of negative 1, I have an output value here, but this portion of the graph is not left continuous, right? This is the left part, or approaching that x value from the left, it's open here. So f is right continuous if the limit as x approaches a from the right of f of x equals f of a. And the same thing is true on the left side. Of course, we have an fraction of this. This does not work in this particular example because this is not true, right? The limit as we approach a from the left of f of x in this case is not equal to f of a. So how about again, going back to the greatest integer function, if I were to graph it, try to make it more clear here this time. This function, oops, that should be a 2, is left continuous, right? Because is right continuous, right? As I approach the output value on the function coming from the right, it's continuous, but coming from the left, it's not. Okay. Let's continue on here. I'd like to talk about the intermediate value theorem, which is one of our important theorems. The intermediate value theorem we call IVT is for continuous functions only. So if f of x is continuous on a closed interval from, let's say, a to b, f of x takes on every value between f of a and f of b at least once. So let's say I've got a, and here's f of a, and b, and here's f of b. All that means is that the function has to take on every output between f of a and f of b. So let's say, for example, there's a value c in between. That means that somewhere along the curve, right, f of c will be between f of a and f of b. All right, so let's look at a practical example here, requiring a little bit of vocabulary. But using the IVT, or the intermediate value theorem, show there is at least one root. That means a solution of the function below on 0, 1. And apparently, I didn't write down the function. So I'm going to make one up. I'm going to go, I might have a problem here. Let me pause the video here for a moment. Let's see if I can pause it. Well, I can't. Okay. Well, I don't have the function in front of me, but let's say, for example, I've got a function that passes through, oh boy, this is going to be kind of rough, but whatever. Let's say here's x equals 0, here's x equals 1, and the function comes up and through like that. It might be a cubic or something, I don't know. Let's say this is 2 and this is negative 1. All right, so what I can say is that since f of 0 equals negative 1 and f of 1 is 2, and on top of that, the function, which I'm guessing is a polynomial, is continuous. All right, that means that I have to meet every output value between f of negative 1, f of 0 and f of 1. Therefore, by the intermediate value theorem, there is at least one value, let's call it, I don't know, c, such that f of c equals 0. Now, what is a solution to a function set equal to 0? Well, or in this case a root, that is an x-intercept. So therefore this point would have to be the point c comma 0. Okay, we'll get into more with the intermediate value theorem later. But this is the beginning steps of using the intermediate value theorem, which we will do pretty much for the remainder of the year. All right, that's 2.6, day number 1 on continuity. Have a good one.